you all from? I know some people have found out already. So I think from how many people? Oh, that's a lot. Okay. IASC. How many from IASC? 2. And the others?
IIT Kharagpur.
IIT Madras.
Who are you working with?
Samir Choudhury.
Samir. Okay. So that means the representation is just a few places in India. Okay.
So good morning and welcome to the morning session. The first lecture is by Professor Pravabati.
Okay. So let us start where we left off yesterday. After speaking to you at the end of the lecture, next to some of you, I have the sense of that you are questioning what is the need for doing all this. So as I give the lecture, please ask me why are we doing this. It's important to know is there any gain, is there any benefit in approaching the analysis of this matter. Okay, just to summarize, yesterday I introduced for you the overall view of how we do extraction of physical information from cosmological data, and that process, at the foundation of that process is the modeling the cosmological data as random fields. That is how we have been doing it. And in order to do the extraction now using random fields, we need to construct statistics, basically, which are functions of the random field functions. You construct those which allow comparison between theory and observation. And you have all been listening to talks of the power spectrum, which is the one of the simplest statistics that you can construct from the data. That is what you have all been listening to, I guess, in this lecture also. And I am trying to tell you of statistics beyond that. And the need for beyond that is there is more information. When the field is Gaussian, power spectrum is enough. But when a field is not Gaussian, power spectrum is not enough. You need to know, just like when you draw the probability distribution function for a random variable, if it is Gaussian, you know the distribution completely if you know the mean and the variance. But if the probability distribution is not Gaussian, you need other variables are there to describe the probability function. So you need statistics beyond power spectrum. Okay, so for that purpose, the approach I am adopting is that we look at random field and we look at its geometry and topology. And what I have done yesterday is to systematically construct a way to describe the geometry and topology information. Okay, so this is where I left off. We had defined in order to define, given a structure in some space, I had defined how we can quantify. The last point that I left you was how to define the elongation. Okay? And that was the Minkowski tensor, the contour Minkowski tensor. We are dealing with dimensions. And just to give the concrete example, let us look at the ellipse. Okay? So this is where I ended yesterday. And what I wanted to show you is, so suppose we are given an ellipse whose major and minor are Q and P, and we choose P to be the larger one. Then you know that there is we can define ellipticity E for the ellipse. So the ellipticity, there are many definitions. So the one I am adopting for this picture is square root of 1 minus Q square by P square. Okay, so that's it. So if it is a circle, it will be 0, and if it is very elongated, it will go towards. So I want the variable 1 minus E. So for circle, 1 minus E is 1 and 0. So what can we do? Given this, you know you can define the position vector all around the ellipse. and so that is P cos theta. Let's use theta as the variable which will parameterize from 0 to 2 pi. So P cos theta, Q sin theta, and x, y, x and z direction. That gives you a position vector. And from there you can construct the normal vector, and you can construct the line element, and you can integrate it. So this I will give you as an exercise, and doing that you will obtain this expression here. So what you see here is that it is a 2 cross 2 matrix which is diagonal, but the two diagonal elements are unequal in general. So, and the expressions for the diagonal elements are given here. So it has this P, the semi-major minor axes are here, and this is an integral over some variable theta, which is not the same as the orientation I defined. It's just a dummy variable which gets integrated out, and this integral can be carried out, and the numerical value of this, it will depend on what P and Q are. So if P and Q are same, then this becomes 1 and this 2 are same. Yeah.
Aspect ratio is just P over Q.
P over Q, yeah. This one. Yeah. Okay. So I am explicitly giving you this expression because what does the Minkowski tensor do is what I am trying to get at. Okay. So this 1 minus E, the plot, let's look at the plot here. So aspect ratio is Q by P, so it goes from 0 to 1. And you can plot how the ellipticity of the ellipse goes from aspect ratio 0 to 1. So 1 being the circle and this being completely stretched out, linear. So the dashed line is how it behaves because it's a square root 1 minus aspect ratio square. Then you can compute this. This can be computed numerically. This is one of the elliptic integrals. It doesn't have a closed form. So you can compute it numerically and you can plot. So the red line is this plot. So ignore the alpha. Alpha is just beta. Okay. The beta is what I had described as the ratio of the eigenvalues. So eigenvalues, because it is in this form already, these are eigenvalues. So it has this form. So what is the meaning of this now? So what it means that given Q and P, there is a 1-to-1 mapping between different Q and P to the eigenvalues. Okay. So that means how can you use this? You can use this in the sense that if you are given some arbitrary shaped curve, okay, then you can use the Minkowski tensor to compute the eigenvalues. Then that eigenvalue, using this relation, you can map it to, you can find what is the QP corresponding to that. And so this is providing for you, given an arbitrary shaped curve, it provides for you a mapping to an ellipse, and that ellipse, it gives you the elongation information. Okay, so that is how we will use it. So here is the mapping already. So if you have a certain aspect ratio, you can read off the beta parameter here. So these are the ratio of that. So notice that when I am doing this, I am not caring for the size of the ellipse, okay? Because I am asking for only the elongation. The size of the ellipse will be contained in the information of the control length, and that is already there in the Minkowski function, scalar Minkowski function. So this is a new information that you get by using this. And so the power will come when we are applying it to randomly shaped shapes. Yes.
We first have a curve and then we try to find the features.
Yeah. So given an arbitrary shaped curve, I will compute. Okay. So some random shaped curve will be given to me. I compute W201. W102. It will have some elements A, B, E, C. Because it's a symmetric matrix, so there is 3 of them. Then I diagonalize it. So I will have lambda 0, 0, lambda 2. Okay. So given these two numbers, I can use this relation and find out, given lambda 2, that means I have to invert these expressions. See? So F is the eigenvalue. These are the lambdas. This, so we will be given this. We will be given this, and you have to find P and Q. Now it looks very complicated, right? It's an integral and this square and so on. But you can prove that it is actually a one-to-one map. Okay, so this I have shown in my paper. If I do that, it will take long time, so never mind. Just believe me that it is a one-to-one mapping. So you can always find an ellipse which maps a given arbitrary shaped curve to some ellipse with given. This is the procedure. So these are all very simple, trivial steps that you can do. Okay. Okay. Then I mentioned that there is this, yeah. It is a curve for every curve. If you have whole, we'll deal with it as two different curves. Yes. Yeah. But okay. Ask me later. I will point out little bit more subtlety which I don't want to get into at the moment. All right. So now, if I have many curves like this example here, where you may ask, is there an alignment between these curves, right? So to get that information, what we do is we calculate W102 for each of the curves, and you can add them up. Because this is a tensorial quantity on flat space, you can add up component by component, and you will get a final W102. And the procedure, geometric procedure for that, what we are doing is, for every curve, you can map it to an ellipse, and then all of them join together again gives me a combined ellipse, and that is this. And if this final ellipse, it has some elongation, that means if Q and P aspect ratio is not 1, then there is some elongation. So that is how it gives the information about alignment. Is there alignment in the data? So the same thing, so now in order to quantify, I have to introduce parameters. So by capital lambda 1, sorry, again this is lambda 2, these are eigenvalues of this tensor which is added up. And I can define a ratio now alpha, which is lambda 1 by lambda 2, which gives the elongation information. So if there is only one ellipse, alpha and beta are the same, and if there are ellipses, then alpha is different from beta. And I can also define an orientation angle phi, which is different from the previous notation, that was var phi. And so this is how we can extract all this information using this.
Ma'am,
Yeah.
what is the difference between alpha and beta?
Alpha is, I use alpha when there are many curves. So there are many structures here. If I am interested in only one structure, then I will call it beta. Okay, the elongation. And if I am doing this summation and then finding a single Minkowski tensor, which is a summation of all of them, and then finding out elongation or alignment, then I call it alpha. So in the trivial case where there is only one curve, they are same. Okay, so is this clear till here, everybody?
Ma'am, is it area preserving?
Sorry?
The mapping is area preserving?
This one?
Yes.
No.
The shape you are mapping to an ellipse, is that area preserving?
It won't preserve area. Okay, shall I move on? Now I move to, here is a summary of whatever we have studied so far. In terms of the new information, so scalar Minkowski functionals are there. They have whatever information they have. Then from scalar Minkowski functionals, you define filamentarity, which quantifies elongation. Then for individual structures, the new thing from the tensor is that you can look at individual structures and look at their elongation and orientation. Then for the combined set of structures, you can quantify the alignment and their orientation. So this is the, yeah.
What do you mean by orientation angle of the alignment? of the
no,
totals.
yeah. So here, this picture is what I mean by the orientation. So here, if you find that the ellipse, so in your chosen coordinate system, this is given some random, some coordinate system is there and these shapes are given. Then you do this mapping and then you do this mapping. So there is so in this example, there is an elongation. In this example, pictorially, you are seeing that there is an elongation, right? So you might want to ask in what direction is the elongation. So that is what I mean by the orientation direction. Is that clear? Sorry? Okay. So, so imagine this is an ellipse. Okay. So in my coordinate system, something x, y. If I place it like this, there is a sense of that along this line, which has a direction with respect to x-axis and y-axis, the elongation is there. Or if I choose another coordinate system which is aligned like this, then I will say it is aligned with the x-axis. So there is an information of what is the orientation of the elongation. Is that clear? If it is a circle, then there is no such thing. Okay, circle, all directions are equivalent.
So, first from that many curves you are transforming each of them into an ellipse, and then combining them, those all things.
Yeah. So you don't have to transform to ellipse. That's why I showed an arrow directly here. Whatever all the computation is being done at the matrix level. So W1, 2 for each of these. There you are adding component by component. So you don't have to do this way. But you can do it this way and come here, or you can come directly. They are equivalent. But the final thing is that finally you will get one single ellipse, which will have based on your coordinate system, it will have the orientation information and what is the degree, okay, P by Q, aspect ratio, what is it? Is it very elliptic or not elliptic? That is the quantification. Is it fine now? Yeah.
So the parameter alpha contains information not just about the relative alignment, but also about the individual elongations of each of them. Each of the individuals.
No, when we are averaging or adding up now, we are condensing all their information. So extracting out individual structure information it's a many to one mapping. So it's hard to find out. So effectively, you will say I will not say impossible, but it will be very hard to extract individual information. That's why we want to use both beta and alpha. Okay, shall I move on? Alright, so far I have been, this was my, so now, so far we have understood the concept of structures and their morphology, and also many structures, we have introduced all the concepts. So now we want to apply, because our goal is to apply to random fields. So let us start with some function. How do we do it? Because a function is a function, it has values all over. So first we have to define the structures and then look for its morphology. So to do that, the concept used is excursion set or level set. I am sure you have all used it or encountered it at some point or the other. So what is a level set? So let's just imagine a function, some function, this red color is function, this is a picture on Wikipedia, you can find it. So some function on the xy plane. Okay, so the z-axis is the function value. So you can say, let me decide on some value, new one of the function, and I will include points. I am interested in those points on the xy plane where the function has values above that. Okay, a value above that chosen level. Then I look at those the subset of space where the function has values above. Then if I look at it from above, it will look something like this. So sorry, this picture looks a little enlarged from here, so it's not to scale, but you get the idea. Now if you go to a little higher level, mu 2, which is higher than mu 1, then your set will look like this, and so on. If you go higher, it splits. So these are what we call structures, and they will be what kind of structures are there will depend on the level that you are choosing. So we want to study the morphology of these structures. Is that idea clear? Okay. So this is for some known function. Okay. Let's do it for a toy example. So here I have a function fxy, which is sin x sin y. If I were to plot it in some range of the space of my xy space, it will look something like this, with values ranging from 1 to -1. So here are these are the excursion sets. Okay. So I choose from above, I choose nu equal to 2.5. So I will have a level somewhere here. So I will get my space, now the subset of space I am interested will become these dots. Because these are the regions where the field or function has values above. So given this set, then I can ask how many connected regions are there. You can count 8. How many holes are there? 0. And you can calculate the area. I was too lazy to calculate the area, but you can do. Then you can count the calculate the perimeter. Then you can ask, okay, what are the beta for the individual structures? There is just one beta because they are all identical. So beta is 1 because it's a isotropic shape. Hole, it's not applicable, there is no hole. Similarly, now as you go to higher threshold, you can do this calculation. So here at some point at nu equal to 0, there is a transition. So now the entire set becomes included and there are holes in them now. So number of holes becomes 8. Number of connected regions is 1 because the entire region is connected. It's a very highly multiply connected region. So you can do this calculation. Oh, I'm sorry, this is wrong. Beta hole. Oh, shape. Yeah. Okay. So the shape parameter beta for connected regions and holes, they are all 1 because this is isotropic. So now this is the kind of game you can play. Now you can see that what you observe is as you change the threshold, this is, I call this as a threshold, okay, the level value, field value. As you change the threshold, these quantities, Betti numbers, the area, perimeter, is there a formula that they follow? That is the question that you would be interested in. There's a pattern, right? So there's an order in this thing and you can calculate. So the goal is to apply to random fields. So here is an example of a 2-dimensional random field, and here is a set of similar to the previous image. Here I am starting with a level which is high here, so just a few peaks are seen. Black region are the excursion set regions, white are excluded. Please ignore this whatever plus sign. So as you come down now, if there is a systematic change, and finally it comes like this. So now you can see that you cannot just do things visually, you need a way to compute it. And you can also see that there is a systematic way in which you are changing. So we want to ask the question of whether we can we find analytic formula for the area, perimeter, Betti number and so on as a function of threshold. So these are the two questions that we will ask now. Okay, so how do we calculate them, right? Okay, so the method that I am going to describe, so clearly here at this stage you can pause and think for yourself, if I am given such a random function, can I devise a way to calculate these quantities? How will you calculate the area, for example? You know already, so if your answer doesn't count. Yeah. Any suggestions? Okay. So you have some area with pixel, and the field has many different values. So given this, I equal to 1 to n, j equal to 1 to n. This is my region. How will I calculate area? Summation of all pixels. You will know the area of each pixel, then you will count, assuming that you are using equal area, You will count how many pixels are there where your values are above. So you can do that. Similarly, if you have your excursion region will be something like this, then you can calculate the perimeter. So, but you have to do something smarter to calculate this, because this is a numerically a hard thing to calculate because it doesn't converge. But anyway, so I know of two ways how we can calculate. Yeah?
When these pixels are covered partially,
Yes, that is the issue. There will be numerical error. So maybe you can say, okay, partially covered, you will say, okay, how much fraction is covered, and if it is more than a certain fraction, you will count that pixel to be included in the line. If not, it will not be. So you have to do all this. So this is the contour is complicated. But
So, we can do this, right? If the value is above and below the threshold in two
Yeah.
different adjacent ones, then we can draw a line to the midpoint and.
yes, that is done. That is done. So now you may think there is some numerical error. Now you may ask the question, how can I minimize the numerical error? How will you minimize the numerical error?
Increasing the grid pixels.
Increasing the width. So yes, people have tried that, but you can show easily that that doesn't converge. Even if the pixel size goes to infinity, the answer does not converge. So that is one of the problems with the calculating contour lens. Yes. So I will give you the reference for that. You can read it on your own. But you need to do some interpolation of the field values. You have to do a little bit more work to calculate. Okay, so what I am going to describe now is not that method. There are two ways. One is this. We actually look at the pixels, identify pixels which belong to each contour or belong to each excursion set, and do the calculation. This is one way. This will take many more lectures to go through. So I am doing the easier way, which is to use the field derivatives and do some process which I will describe now to compute these quantities. Okay, so that is what I will do. Okay, so this is a method which was, I think one of the steps was first given by Smolzing and Booker and Smolzing and Gorski in these papers. All right, so how do we do this? So in order to do this, so we know that the problem is identifying the excursion set boundaries and what pixels are included. So the first is that I am given the function. I need to express all my geometric quantities in terms of the function, right? So here, sorry, I changed the f to u because these are existing equations and I didn't want to change my notation. So u is now my field. It's given to us as a function. So I need to change the normal vector, tangent vector, and the geodesic curvature into expressions which are dependent on the field. Okay, so that's the first step. So for that you realize that the normal vector, normal to any function, is given at any point x is given by the gradient. Okay, so this is the first thing to realize. Then we will also need for a next step tangent, and the tangent you can realize that the tangent is given by a 90-degree rotation from normal. Okay, so but you have the choice of choosing this orientation or that orientation. So let's choose one and be done with it. So to express that, I write it as this Kronecker epsilon. Levi-Civita, the 2x2 Levi-Civita matrix, and this expresses the rotation. Then we need the expression for kappa. Okay. So kappa, again, these I will give you as exercise. The kappa, if you remember, the question I wrote in yesterday's slide was that it tells how the tangent is changing as a function of the arc length. So the tangent itself is first derivative, and I am asking second derivative. So it is a quantity which is given in terms of second derivatives and first derivatives of the field, and this is the expression. So these three expressions we need, but these are general expressions. It doesn't tell which contour and so on, right? This is given a function, I can calculate these quantities. So, but I need to choose the level. Yeah. U1 is first derivative. First derivative, okay. Sorry. So I am doing two-dimensional manifold. So there are two derivatives. So U1 and U2, two index means derivative respect to one coordinate, second coordinate. And 1, 2 are the second derivatives. And there are three of them, 2, 2, 1, 1 and 1, 2. So there are three of them. So is that clear? So far this is just writing these quantities in terms of the field. Now let's connect it to the discussion center. Next. Okay. So basically I want to calculate these for the iso field contours. Now field contours are defined by the level u equal to mu sigma naught. Okay. So this is my notation. So you can say the field is fluctuating, it has fluctuations like this, and I am measuring in units of the sigma. If it's a Gaussian field, it will be most of the peaks will lie within say 3 sigma, okay, 99%. So it's useful to calculate the sigma naught of the field, the variance of the standard deviation of the field, and express the levels in units of that. Okay. So nu will be expressed, the answer, we will express nu in like 1, 2, these are the typical levels. Alright, so for our quantities, so these are the three scalar Minkowski functionals, and this is the Minkowski tensor, the contour one. These are the, all I have done is introduce the kappa here, and I have introduced n hat cross n hat into a matrix, which is, and I am just reminding us that we have to calculate these at these regions. Similarly here, all of these will have this divided. Okay, so now you can see that clearly this is going to be hard, because identifying those contours is hard. So from this step to next step, can you think of, anybody think of some way where we can put the formula in a nice way so that we can implement it numerically? Any suggestions? Okay, so no suggestions, so I will tell you the suggestion. So I said that identifying contours is difficult, so we will introduce delta function. Okay, so the level is basically identified by a delta function, right? Where the delta function of u minus mu sigma naught. So if I introduce in my formula here ds, an integral over du with a delta function u delta of u minus mu sigma naught, then this ds and the du can be changed into area integral. Okay, so we can change it into an area integral, and there will be a Jacobian which is proportional to the tangent. Okay. So now this is the crucial step. I change from line integral to area integral. This will now allow the pixel counting. So we don't have to do the contour identifying lines and so on. So then the expressions now all become area integrals. So this one was already area integral, whereas this and this are now changed into area integral. Sorry, this should be m. M is my manifold. Okay, so given a random field u or any function actually, these equations can be implemented numerically. So now we need to numerically approximate the delta function and include that in our calculation. So now at this stage I want to pause, and I have put this star to remind me that I should pause and ask you, can you find some flaw in this calculation? So I am proposing an algorithm, and and the flow has to do with the M. So as far as these calculations are concerned, M is two-dimensional space. So now I want you to think about what the answer will be. Some problem with this computation. What happens if my manifold size, so you are all used to data which is on a finite region, right? Always data is like that. But imagine that the space is expanding, your data size becomes larger and larger. Manifold is extending all the way to infinity, R2. Then what will happen to these computations? I'm just asking a statistical physics question. So you will find that won't it go to infinity, all of them? Because if you imagine your random field is something which is defined over all R2 and extends all the way up to infinity, and you keep integrate over all quantities all the way up to infinity, it's going to be infinite. So you have to define a density. Okay. So in order to do that,
But numerically we cannot go to infinity, right?
we cannot go to infinity. Yes.
So numerically that should not be a problem.
That should not be a problem. Yeah. But if you do a computation with your data, and if somebody else does a computation with another size data, then you cannot do a meaningful comparison.
So it is size dependent.
Yes, size dependent. So you want to scale out the size. So we want to divide by the area of the space that you are looking. Then you can take it all the way up to infinity, because that ratio will be meaningful, it will be finite. Okay. So since now we know how to compute it, and in the tutorial Fazlu is going to walk you through the computation, various stages, but I'll take that for granted that we have already implemented this. And before applying to random fields, using that computation, I want to show a comparison of the shape information between just the filamentary from scalar Minkowski functionals and the Minkowski tensor information. So let us look at two examples. So we know from the definition of filamentary and beta that for a circle f is 0 and beta is 1. And similarly for a total filament with no area enclosed, f is 1 and beta is 0. So if they have identical information on the shape, then a structure, they should have for different kinds of shaped structures, we should get similar information from both of them. So let us see if we do that. Okay, so these are the level sets which I have drawn superimposed on each other. Each line is showing a level set for a function which is constructed from two-dimensional Gaussian Gaussian function with 4 peaks. Okay, so the Gaussian peaks are located at these regions, and so it is like a mountain peak with 4 heights, and I am drawing contours around at different levels. So these are the levels. So you can see. So here for these different excursion levels, you can calculate the various filamentarity and so on, beta and alpha. So one more point that I have to mention is that the previous formula that I showed you does not give beta information, because I am integrating over the entire space. So it only gives the alpha information, but here I am going to show beta calculation, which is by using actually connecting pixels. Okay, so I have used 2 different methods to compute. Alright, so this is on the left hand side are these shapes, and on the right hand side are the various parameters that we have calculated. So let us look at this page. So the threshold from 0 to 0.6, so 0 to 0.6, look at the contour. So point 2 is one single contour, right? So it is one single structure. The next is point 4. This is point 4. So the point 4 contour is also one single structure. Okay. So all the way up to roughly point 6 here, maybe just before point 6, it is one single structure. Then as you go above that, now it splits. This one has split. So above point 6, we have one structure and two structures. One which is quite round and one elongated. And so on. As you go to higher, you can see that at point 8, we have 4 different structures. So let's look at the first phase up to 0 to point 6. There is one structure, so alpha and beta are the same. There's only one structure. And so what am I getting? The filamentarity, let's look at it first. The filamentarity is this magenta. It is going from low value to high. Okay. So high means more filamentary. So you can see low means it is more not as filamentary. So can you agree? Do you agree with this? So the outer curve is at point 2 here compared with say point 4. So here it seems to have shrunk, right? It's a little bit more elongated. So you can see that visually. So it has, that's why it is increasing. Okay, as it go up. Similarly, what about, so this is a very elongated structure. So alpha and beta, let's look at alpha and beta now. Alpha and beta are also showing values which are deviating from 1. That means it's an elongated structure. And they are the same till 1. Now at this stage, the structure splits. And the filamentarity here is the average over all the filamentarity values. But what we can see is that so filamentarity still remains, maintains roughly the values. But you can see one of these, let's look at blue. This one is basically the beta value for this. So it is now saying that that structure has split and it is tending towards isotropy, which you can see by eye. Whereas alpha is red here. So alpha is red here because there is alignment between these two, right? So it is still saying that okay, there is some alignment between them, and so my value is going to be low. So this is how, similarly, you can interpret this part. So this part, it has all of these are now individual structures and they are all highly compact, circular, and so the F value has gone close to 0, and all of these tend to 1. So this is a structure which does not have any, which is nice and no ambiguity. It's nice elongated. Now the next example will be where the difference will come up. This is an example of a structure. So it is long. If you look at it like this, it is elongated, right? But it is curled in on itself. So how does alpha, beta and F interpret it? Okay, when you compute. So F will still say, okay, it is elongated. Okay, it does not know that it has curled in on itself. Whereas alpha and beta, the values are here. So alpha and beta have known that okay, it's curled in, so it's tending towards isotropy, and so my values are here. Okay, so this is the difference. You can look at these at leisure. I will give you the slides, but let us move on from here. So the conclusion is that F, alpha, beta, depending on the kind of structure, they can give the same information, or for structures whose center of mass is like outside the body, then for those there is new information. Okay, they are complementary to each other. So it is very useful when we are looking at random shapes. For example, applications to bubble shape, ionized bubble regions, you want to quantify shape. There is always a problem. Or large scale structure, there is always a problem. Then we can use these different information and understand the shape better. So they complement each other. But the new thing from alpha, from the Minkowski tensor, which is not there in F, is the alignment and orientation, which I have not plotted. Yeah. What is new? Oh, this one. This is the level. So I have the function. I'm doing level.
That is very easy.
That's what. Well, when you do numerics, you have to. It is so. You are talking about this jump.
Yes.
Yeah. These are jumps because clearly they are structures as they are connected and then they split. So there is a jump for that. Now keep that question and ask it for random, random fields. So there you will not see any jump. So you can ask what?
So is there one correspondence between these parameters and shape? For example, if we know these parameters,
Yeah.
is there a unique shape or
Very good question. So it is not unique. Okay. For example, even for the isotropy beta, let's say beta. Okay, beta equal to 1 case. Beta equal to 1. It just says, okay, we will start with a triangle. Since we are doing smooth curves, we will smoothen this here. This or a square, smoothen, and pentagon. All of these will give the same beta. Okay. It does not recognize these extra additional shape differences. It just recognizes m-fold symmetry. So as long as it has m-fold symmetry with m greater than 1 or greater than 3, it gives the same beta. So that also includes structures which are of this type. And you can also put more patterns. All of this will be this. So it's not one to one. It's like infinite to one. Okay. So then that opens the thought process for you to say, okay, if I want to distinguish them, how will I do it? Right? Fitting to ellipse is not going to do it. But by looking geometry and topology, you can do it. You can count, for example, number of zeros of 3. Okay, that's one thing I'm calculating now. So this is you have the geodesic curvature for these. You can ask where are the points where it has zero. Because when you have a shape like this is a positive curvature, negative curvature, so there is a 0 here. There is not a 0 here. They always come in pairs when the curve closes. So if it has many, then the number of zeros is going to be high. So can we calculate this?
the derivatives of
Derivative for second, third, derivative derivative. So you have to keep looking at it. But to compute though is very hard. That much I can. Okay. So there is you can see that there are many questions you can ask for if you want to quantify shapes better and better for application to cosmological data. Okay, so that is about the shape information. Then just one more point for the random fields on the sphere. So far I have been discussing only R2. On the sphere, the Minkowski tensors, the R, position vector is not defined. Right? On curve manifolds, position vector is not defined. It's only defined in local regions where you can say, okay, this is, for me as far as I am concerned, this is flat. So all the Minkowski functionals will not, tensor Minkowski functional tensorial ones will not be defined, well defined, but the translation invariant ones are well defined. So it doesn't, so for the quantities we are interested in, no problem. But one important change is that the Euler characteristic. So earlier for flat space, we had kappa integral ds by 2 pi is 1, right? We counted. But on curve space, it is no longer 1, and there is an additional term which depends on the area enclosed within the curve, and this r, r square is the radius of the sphere that I am taking, and so this is the Gaussian or Gaussian curvature. So this quantity will change. So you can either find out this area and use chi, or you don't. It doesn't matter. You can just compute this part which we call W2, and we can still use that. Okay, that is still a good statistic to use. So in whatever follows, we will use only W2. We will not worry about this because this information is there in the area anyway. Okay, and this is what you learn when you do parallel transport on the sphere. This gives you the deficit angle when you bring a curve along a closed loop, and you find that is proportional to the area enclosed within the curve. Okay, so with this now I have given for you all the definitions and properties, and I have given how to compute for a given function. It may not even be a random function, random variable, random field. So now we will do some analytic calculations, analytic part, because we want to know, like the question I asked earlier, as a function of the threshold, can I obtain analytic expressions for these statistics, morphological statistics. So the first question is, can we relate the nature of the field? By nature I mean Gaussian field, Rayleigh field, or log normal field, and so on, that to these morphological properties. And the second question is, of course, how can we use this for physical inference, which this part I hope to cover in the next lecture. Okay, so let us now discuss a little bit about calculating analytic expressions. Okay? So how will we calculate analytic expression? By analytic expression, I mean ensemble expectation values. So for that, what are you going to need? You are going to need the probability distribution. And let's take a look at this, the formula. We want to find the ensemble expectation of these quantities. So now this is an integral over various regions. It's a geometrical quantity basically, which is extended in space. So the ensemble, and this is all the relation to the field is going to come from the field U, the nature of the field U. So I need to be given the nature of the field U, I need the probability distribution for U. But then there is first derivatives and second derivatives also. So I need, and they may be correlated, we discussed it yesterday, there was that covariance between the field and its derivatives. So, and my statistic is a function of U, first derivative and second derivative. So at least I need the covariance matrix up to second derivative, right? Because now in order to do ensemble expectation, what will you do? You will say, okay, I am integrating over all U, U1, U2, U1, U2, etc. and the probability, joint probability of U, U1, U2, etc. and this. And can we do that calculation? And the answer is very, actually, it may look very complicated, but you can do it. So, this calculation was first done by Tomita in 1986. Not in the context of cosmology. He was studying random interfaces, condensed matter, I think. Okay, so to proceed with this calculation, we need to define, let us define the row or column matrix X, capital X, whose elements are U, U1, U2, etc. There are 6 elements. So these are my random variables, random fields, but random variables. Then, let us, to proceed, we are going to take Gaussian isotropic field. Okay. So we need the joint probability distribution of X, and it is given by this form. Okay. So you recognize, so I am still using small p here because this is supposed to be at one point in space. But because we have yesterday's lecture, I said homogeneity tells you that all points are equivalent, then this same probability will hold at all points. That is what we are using. So 2 pi to the power 6, determinant of the covariance matrix, and e to the power this form. So everybody is familiar with this. So now we need a form of the covariance matrix. So the covariance matrix, you may ask, where is this coming from? Okay. So let us go back, maybe just look at the this word, going back to look at the slide for covariance. This is where I have defined fields and so this is basically F. So the 0, 0 element is sigma 0 square. Sigma 0 is the standard deviation or variance of the field, and 0i is F and Fi for the covariance between the two first derivatives. So, so these things I don't have the proof for you, but you can prove it. You can prove it to show that if the field is Gaussian, not Gaussian, sorry, isotropic, the covariance matrix will have this sign. So it will have. So this is the autocorrelation of f of the field. This is the autocorrelation of the first derivative, autocorrelation of second, and individually each one of them. Okay? 1, 1, 2, 2. So these factors 6 and so on come from the definition of the covariance. So for this lecture, I will ask you to take this for granted, and this half is because you are assuming the first derivative covariance of one derivative is the same as the covariance of the second derivative. Second derivative means field derivative with respect to second variable and first variable, they have the same covariance. So that there you are incorporating the idea of isotropic field. That means the two derivatives in different directions, they are statistically they are the same. And f does not it does not correlate with the first derivative. The field does not correlate with its first derivative, but the field correlates with the second derivative. Okay, because you can move one of the second derivative, you can move by what? Total derivative. You find total derivative minus move the derivative onto the field in the first place, and you get a minus sign here. Okay, so that is why this expression comes. Okay, so if we have this expression now, then what do we do? Simple, straightforward. The ensemble expectation of any statistic constructed from random variables of this type, they are nothing but integral over all the field values and P and V. Right? So we just have to calculate this. And so for our 4 variables, for our 4 statistics, they are this. So this is going to be done at every nu. Okay, so now actually you can do this integral by hand, and I think I should include this in the exercise sheet. You can do this, so you just plug in the form of P here, which is a Gaussian, and because of that covariance form, most of them will split out because there are many zeros there. So this expression here, this will split out into a very nice long sum of Gaussians, product of Gaussians, which will, these 3 will be nice, very simple. The only thing which takes a little time is this second derivative part, and you can calculate this by hand. Oh, there is a mistake. This Papa should not be. Sorry. When I give you the slides, I will change. I seem to have just copied from here. Here it is correct. Yeah, I should have put this. Okay, so now we are ready to look at the final answer. Okay. So I was referring to the area, right? So now one important thing that we need is that one point that I should mention here is this is an area over space. This is an area over field space, field values, first derivative and second derivative, all of them. So now to do this integral, homogeneity, we'll use homogeneity and say that if this P is the same at all x, all spatial points, then I will interchange the area integral with the x integral. And I will compute the integrals over the field variables first.
So what is the C in CMT?
CMT is the contour Minkowski tensor because there is only one, right? I am not doing the entire thing. So I will move this area integral outside and carry out that integral, and that integral can be done. But there is an area integral, and that area integral will be, gives you the area of whatever your space is. Okay? And that integral will go to infinity if you are taking your space to be extending all the way up to infinity. And that is why in the previous slide previous slide, I explained that we have to divide by the area to make this quantity conversion. So what we are defining is morphology per unit area. Okay, so now let us look at the structures. Yeah. So the first one, area, it has this complement of the error function. Okay, as a function of mu. So our question is always, as I change the level, so this is this complement of the error function. So the plot of this is here, the red curve. Okay. So complement of error function is 1 minus integral of the Gaussian function from mu to infinity. So that gives you this. Then the perimeter, for the perimeter you get a Gaussian function. Okay. So notice that there is the shape dependent, shape means as a function of the level there is a function, and I have written, I wrote proportional because I was not careful of carrying factors and so on. That's why it's proportional. These are just numerical factors. So I have this quantity 1 by RC. And you can see that this is perimeter, so it is units of 1 by L because of the per unit area. And RC was defined yesterday to be sigma 0 by sigma 1. Okay, that is the typical length scale in the field. Then the counts is given by 1 by RC square, nu times e to the power nu square. So these are the plots where I have factored out the RC and I am plotting only this part. So W1 is the green one, is Gaussian function. W2 is this one, which is this blue function. I have scaled out the amplitudes, which are these quantities. Okay? Yeah. So any question till here before we interpret?
What structures previously in the slides you showed, you considered some structures and then
Yes.
calculated the W which was
Yeah.
what structures are you?
Yes. So, what structures? Okay. So let us demonstrate that by an example. Yeah. So these are the excursion sets for a. This is a Gaussian random field plotted in a small region of space. And so for each level, so this square corresponds to, imagine that the field, the region over which the field is defined is plotted here in this square. Yeah.
So this field can be, suppose like in cosmology, this can be the density fluctuation.
Yes.
Material.
It can be cosmic microwave background, semi-temperature field.
Or
It can be reionization 21 centimeter. I'll talk about that in the next lecture. Or it can be matter density, baryonic matter, galaxies. It can be any of those cosmological observations. But the assumption, this is, we are not applying to data in what I am showing now. I am asking a more mathematical question and asking, if I am given that the field is Gaussian, can we calculate? Is there some regular way in which these morphology change? That was the question. And so this generic example tells you that, so as you change, so let's just do a simple exercise. Okay. So from our top to bottom, if I change different thresholds, and these are the external sets where I am saying. So you look at the area. Let us try to estimate what is the area. So this area is basically top to bottom. Yeah. Yes. Let's assume this is isotropic. So you can calculate, look at this area. So if my area is the white region or the black region, so here it is very less, right? If you look at the area, it's increasing, isn't it? Black region is increasing, and then it goes to high. So this is what you are seeing as, this is the negative threshold side. So you are seeing it as a going from minus infinity, from 1 to 1. So this is threshold. So area from negative threshold, let's say minus 3, Can you see that visually? Can you see with that? Okay, let's start from here. On the negative side is this. So the entire, most of the area, the excluded region, which is white, is very less. So if I calculate the black area divided by the total area, it will be close to 1. That's why it is close to 1. Now as you go here and then slowly move this side, the area fraction is decreasing. Right? And then it tends to 0. And that is the complement of the area that we saw, that we obtained analytically. Next is the perimeter. Now you look at the perimeter. This is for one realization. What I showed is ensemble expectation. That means I have one realization like this, another realization, I average.
Real life we don't.
Yeah.
How do we calculate?
How do we calculate this expectation? In real life, we cannot calculate. We can calculate. Okay, in the tutorial, the first one will show. So for that, I'll answer that question a little later. Let's do this visual thing first, and then I'll. Oh, sorry. Next, this is tea time, right? 11:30.
Like
Okay.
10 minutes.
5. Okay. 5 minutes. I think I'm ready. Okay. Now let's look at the perimeter. So here the perimeter will be the contour enclosing this. So it is no here. Look at here. The perimeter will be the contour enclosing the white. It's no on this extreme. Okay. So go here, go here. Now as somewhere around the mean, which is 0, maybe this is the. Here you see the contour is very long. So the perimeter is going to be. So you'll have some value here, and you will connect smoothly. This is what you do. Okay. And for a Gaussian field, it is Gaussian, e to the power minus. Then let's look at the Euler characteristics. So here you are. These are connected waves. You count 3. Here you see one connected, entire thing is one connected region, and you have a few poles. So, I will plot, let me plot it here. Plot it here. On this side and on this side. Poles, when you, in the Euler characteristic, it is B0 minus NC minus N as a minus sign. And there is excess of poles, Euler characteristic will have minus sign. It goes, it is on this side. This is mu, this is negative, and this is positive. Here it is slow. So on these two extreme ends, this and this, you have the value here. And now I need to connect intervene. Here, don't know if you can see here. This is like they are equal. It goes to 0. Then somewhere in between here you can see lots of poles. And here maybe drop. So it goes up, goes down. Get it? And if the field is Gaussian, this functional form will be mu into the power. Get clear? Okay. Now the remaining point that I must mention is, where is cosmology? Where is the cosmological parameters? Cosmological parameters. So given the nature of the field, this shape is you can do what? The cosmological parameters, you know, if there is lot more dark matter, if dark matter is cold compared to warm, you know that a warm dark matter structure is erased. Then you will see, you expect that the counts will be fewer. One of them, say cold dark matter will have more. So those things will show up, and those will be affecting here. So this RC is dependent on sigma 0 and sigma. What are those quantities? Those are these spectral properties, the cosmological parameters will enter in. So you have studied how spectrum, these quantities can be related to integrals of the form. So that is why here I can jump into the question of, if you are going to constrain cosmological parameters, is this method good compared to Gauss spectrum? So the answer is Gauss spectrum will be more powerful, because in the Gauss spectrum you are splitting it into modes, and each mode we know how much power it is. And each mode will correspond to some length scale, and the physics of some property of, say, dark matter bonds will determine some length scale where its effect is strong. And that effect will be easy to pick out when you are looking at the Gauss. But here you are integrating out the entire Gauss. So that means that information will get mixed up with other information, segregating it out will not be that easy. And so for that kind of study, it's better to use Gauss. Okay? But the information is not that it's not there, it is there in this. So these will determine what are the amplitudes. Here I have drawn only the shapes, I have removed the amplitude. This, when I plug in the cosmology, it will tell how much structure is there, how many structure is there, what is the perimeter, all of these in the cosmological. Okay, so I think we can pause here. Yeah, sorry, your question needs more discussion. Okay, maybe we can break and we can discuss.